Vous m'entendez bien? Ça a l'air de bien marcher. Super. Un problème de résolu. On espère que la démo va bien se passer. Hein? Eh ben, j'ai pas bien vendu mon talk, on dirait. Toi aussi, c'était pareil. Ah, c'est rassurant alors. Les gens sont tous déjà à l'apéro, c'est ça? J'espère. On va dire que c'est ça. This talk is going to be in English, mainly because it's going to be recorded, and I'm happy that many of us can understand it. So let's start with a quick poll. First, how many of you has an Android? Can you raise your hand? Wow. The majority of you. Okay, cool. So maybe you didn't know, but you're actually running eBPF on your phone every day for security and networking reasons. And now you're wondering, what is eBPF? So in this session, we'll dive into the world of eBPF. What is it? And also explore its role in Kubernetes and how working with Go simplifies working actually and implementing some programs. For maybe most of you don't know me, I'm Donia Chaiehloudj. I'm a software engineer at Isovalent at Cisco. We build projects around eBPF. And I'm also the co-author of a book, which is Learn Go for with pocket-sized projects. So if you're curious, I would be more than happy to handle a PDF book for you. Let's dive into it. So without eBPF, how does it work? If you want to make changes to the Linux kernel, it can be a cumbersome process. You need typically to write kernel modules, which are complex, risky, and require to reboot when you deploy your system. Debugging and testing can be equally challenging. And each change that you're going to make to the Linux kernel comes with potential risk of stability. And if you didn't know, but it can take years before your change that you ask for come into a release in the real world of development. You can see eBPF as the Swiss Army knife of the Linux kernel. It lets us run custom programs inside the kernel, and these programs can observe, modify, or act directly in the kernel on events like, for example, networking, network packets incoming, or file access, without needing to modify the kernel's source code itself. And that's why it's very powerful. As mentioned, everything changes. So because you can dynamically load programs in the kernel, eBPF provides a safe and sandboxed environment for the custom logic that you want to implement in the Linux kernel. You can monitor, debug, secure your system without disrupting it, and it takes only a few hours or a few days if you have more complex programs. eBPF works by attaching small programs to key events happening in the system. As mentioned, when a file is open, for example, you can attach a program that will occur when the event happens. And they're run automatically. You don't have to do anything. Each time there is an event, your program will run. Again, in real time, you can observe your system. And you're wondering, why is she talking about that? It's because it can be very powerful in the Kubernetes world. Kubernetes is at the foundation of cloud-native ecosystem and distributed systems. I bet that most of you know what is Kubernetes, but for those who don't know, it's an orchestrator for containers where you can run applications. And all these systems are built on shared infrastructure with multiple containers running on one single host, all sharing the same kernel. And because eBPF programs run at the kernel level, they aren't limited to individual containers. They have visibility into the entire stack. This means, again, you can do networking, you can monitor, you can optimize traffic with networking across all containers on a host without needing to modify each container individually, but only on the kernel level, and it will impact all the containers. But what makes eBPF even more exciting is the ecosystem that we have around it. There are many tools We had just a talk before from Henrik about security runtime tools that are based on eBPF, but it's only one of the tools. There are many of them. There is Cilium for Kubernetes networking, BCC for tracing, and Pixie for observability, and they all rely on eBPF under the hood. These tools enable use cases, again, such as tracing system events, monitoring network traffic, and securing dynamically workloads, all without impacting application performance. Don't take that as say, because depending on the tool, I just learned that it can impact the performance. So this ecosystem is growing rapidly and making eBPF even more accessible to developer, sysadmin, SRE, or observability team-like. So that's very interesting for that. And today we're going to talk about Go, as mentioned, and why is it useful when you're using eBPF and you want to develop with eBPF. So basically you have your use cases, as you can see. Then you have the user space, which is where you will run and write your application programs. And then there is the kernel, which is not directly accessible most of the time. And this is where eBPF programs are running. And to be able to program, to load these programs, we are using SDK based on different languages. And here, again, we will focus on Go, because I love this language, but not only for that. It's mainly because Go is the gem of the cloud-native ecosystem. So most of the cloud-native tools, are based on Go. You can think about Kubernetes or Prometheus, Grafana, you name it. There are so many of them based on Go. And that's because actually Google developed the language Go back in 2009 to solve large distributed system problems. So this is the language that has been made for that kind of problems. And Go plus eBPF is very powerful and productive. There are many SDK that exist. I mentioned one here because I use it, so I'm happy to present it, but there are others, so you know. And we will explore Cilium eBPF. To write eBPF programs, you will probably start with C code. I know I talked about Go, now she's talking about C. Yes, we'll talk a little bit about C. And you will be able to define the program logic in C, and this code is then compiled into ALF object using Clang, a compiler, and these objects are then loaded into the kernel and attached to the events that I just mentioned that are happening in the system. There is something interesting when you're developing in eBPF and any SDK in the user space, is that you can use maps. And this is, I guess most of you are developers, so you know what is a map, but this is a place where we will store data. And there are different types of data and ways to store them with eBPF, more than 20 of them, like a hash array. And it's very interesting because maps enable us to store the data inside the eBPF kernel from the source and the events. And from the user space, you will be able to take them, retrieve them, and put them, I don't know, in your Grafana dashboard, for example, if you want to measure the number of incoming packets, for example. So that's why maps are very cool. And the development cycle look like I write an eBPF C program, I generate Go objects and methods using some tools that enable it and make our life as developer easier. And then you can write your Go main program using all these objects based on the eBPF program. And then you can run it. And you run it from your user space, and it will actually take all the info in your kernel. I want to show you some of the capabilities of eBPF with some examples. The first one is the tracing. And I will present to you a program that is tracing each time there is a file that is open on my system. So can you see properly? Yeah, okay. So here we have a C program, and it's very simple. It hooks into the sys enter openat. This is one trace point that is actually available on the system, and it will trigger whenever a file is open. And the program will just print using the helper BPF trace print K, just a file is open. Simply, this is very simple. And what I would expect is to see in the trace pipe from the kernel these kind of logs where I have the process ID and the log that I just mentioned with the helper function that is called. But I'm going to introduce you to Go. So I will use one command that is Go generate. It enables to take the eBPF program, compiles it, and then generates Go objects corresponding and mapping to the eBPF program that I will be able to use in my main Go program. And here are the examples of the generated Go objects. We have an open file objects with a program, maps, and variables. And here you can see, can you see my, no, wait, yes. You can see here the type open file programs and a structure with a trace open at eBPF program here. So eBPF program is the type. It's actually the program that we just wrote in C that is mapped to this Go object named trace open at, which is again very powerful because I will be able in my main Go program to say, load this program. So from the Go code, I'm able to say, I want to load this program and I want to run it then. I will attach my Go program to one of the syscall, which is again sys enter open at. And I will log if it's not working. And then I'm going to show you what it looks like in real. I'm not lying. All the files are here that I'm just showing you. I can show you the main here, for example. So you can see here that you can see here that I'm loading the file. I'm using the leak.tracepoint, which is from the library Cilium eBPF that I just mentioned. And one thing that I didn't show you is that I'm just calling the cat on the trace pipe file. So I can show you directly in my Go code what is the output. And I'm going to run this program. As you can see, oh, wait, I'm not in the right directory. As you can see, I'm using sudo because when you are running eBPF programs, you need some privileges because you are running on a kernel. So, you know, you're dealing with some responsibilities. And oh, that's funny. Am I running the right thing? Oh, yeah, this is the logs. OK, there is file opening. I'm just kind of surprised because that's funny. I didn't expect this. But I guess I added some logs that I forgot about. Funny. But yeah, so as you can see, there are some file open. And I didn't log here the file that was open. But you could. I'm sorry, I got surprised. Let me go back. So here I'm running my program. And you can see the output from the cat of the trace pipe. You can see the process ID here. There are some ping, and there is some open file, which is what I want to see here. And the helper that I just showed you at a file opening. And you can see that I'm not opening a file currently when I'm running this program. It's because your system is actually opening a bunch of files to make it run. Another thing that I wanted to mention is that I'm not running, so I have a Mac, but I'm not running the programs on my Mac. I'm using a VM with the Lima tool that enables the virtualization of Ubuntu system here. So I'm running on Linux. Maybe you didn't realize, but yeah, okay. So very happy that it's actually working. And let's go back to the slide. So we've seen that in just a few lines of code, with 2 files, we're able to trace what's happening on my system from my user space, which is where eBPF is powerful. And here we've seen tracing, but I want to show you something else about eBPF. Another capability is XDP. So it's actually one of my favorite features. So XDP, with XDP, you can analyze and filter network packets before they even reach the kernels. So think about processing packets at the earliest possible stage. It means that you can save CPU and cycles and avoid also costly kernel overhead. Maybe you want to drop malicious packets in real life, or for security, or for performance in load balancing, especially in cloud native ecosystem. We know that it's very important to go at light speed traffic. So that's why I think that XDP is very powerful for that. So I'm going to show you XDP in the observability world with, again, a simple example, which is a packet counter with maps. So I can show you also maps, how it works. So if I go there and show you, so I'm going to show you the counter here, and then maybe we can go into the counter IPs. And again, I'm just going to run my program here. One thing that can be interesting, because I didn't show you the full code, I'm sorry. One thing that can be interesting here is this. So this is the map that I'm defining in my C program. And I'm using a type array. So I'm just saying that I will store a counter. And each time I have a new packet incoming, I will increment this counter. Very, very, very basic. And in this map, I'm checking if I have a counter, and I will use this helper sync, fetch, and add on my map to fetch the actual counter and increment it. Very useful. And again, I have my main Go program on the other side, and I'm doing the same thing as before. I'm loading the program that has been generated in Go object using BPF to Go. And one new thing here is that I'm attaching to one interface. Here I choose it0, but you could use any interface that you want in networking. And I'm using this helper link attach XDP with my actual program. So this is the program that is mapped to the eBPF1 in C. And I'm using the interface that I just used before to say I want to attach to it0. So basically what it will do is each time there is a packet coming to this interface, my eBPF program will be triggered and the counter will be incremented. And in my Go program, I'm just logging it and retrieving this counter periodically with a lookup function on the map. And then I just print it here, received the number of packets. And as just shown, so if I run my program, I can see on it0 that I have a counter that is incremented. I'm not cheating. Again, I'm not pinging anything. But because I'm running on my Lima VM, there is like some exchange of packets between my host and my VM. So that's easy. Then we've seen very interesting demo about observability. So just to wrap up this section, we've been able to create a map to say to the kernel, don't actually see any packet because XDP is doing it. And each time there is this packet, XDP will take it and say, okay, you're here, I can increment this counter, and in my user space, I'm able to see this counter. And you can, again, imagine that it can be interesting to see it in a Grafana dashboard, for example, or you can monitor for security reasons if you're not expecting so many packets, or you can observe if you don't have enough packets that something is going wrong on your cluster, for example. Nice. Let's see now the security capability, because this is where it's very interesting for real use cases, I would say, because we are doing monitoring, but security is kind of touchy. And that's very interesting to see with XDP, again, what we can do. And again, it's a very basic example, but this is some things that are actually used in production, just, you know, like for companies like Adobe or whatever, big companies. So this is concrete examples. And for XDP, what I want to do is to attach my program again to XDP. And I'm just going to check if this packet is coming from a specific IP. I want to drop it by using XDP drop when I return it, this constant here. Otherwise, I will let the packet pass. So depending on the incoming IP, I will block it. And let's have a look to the demo again. And let's run it again with sudo. So we are attached to interface hello, which is loop, which is because I will ping in localhost. And you can see that there is nothing that is blocked. And if I ping localhost here, oh, I'm actually on my host, as you can see. So I'm just going to enter my VM and ping again localhost. And I should see, yeah, OK. Oh, yeah, I've seen that. I forgot to fix it. I don't know why I actually printed my IPs are reversed. So it's localhost, as you can see. Okay. So this is something that I need to fix. But it's actually localhost. I'm not cheating. So we've seen that here the number of packets are incrementing again because I'm pinging. And you can see on the other side that we have, oh, interesting, 19 packets transmitted and 2 received. Why? Oh, yeah, sure. Thank you. Cool. Next time I will stop the ping before. You're following. Good. Thank you. Yeah, definitely. Thanks. So we've seen this interesting security. And again, it's actually these kind of things that are used in real tools. So that's very cool. And again, because it's running using XDP, it's very processed. I don't know how powerful you can think about it, but like not even reaching the kernel, that's incredible for very large distributed systems. And the last use case that I want to talk about is networking. I'm not going to show you a demo of the code, but real life, but I want to talk about Cilium quickly. So Cilium is a networking observability and security tool for Kubernetes powered by eBPF. And unlike traditional solutions that rely on IP tables to do networking in Kubernetes, it's actually using eBPF. So it will bypass all the IP table rules when a pod wants to communicate with another pod, but use all these eBPF programs that are running at the kernel level, shared between the different containers. So it will be more performance because IP chain rules, IP table chain rules, it can be very complex. Depending, like I've seen actually customers with 10,000 network policies running on their cluster. So you can imagine how complex it can be. And we just bypass that by using eBPF. And talking about network policy, so Cilium network policy are defined in YAML. Most of the time it's very declarative in Kubernetes word. You have a YAML and you define with a specific security here that you want to be able with front-end pods to communicate with back-end pods and not the external one. I mean, that's very common as a use case, I guess, for you. And we are saying just basically, so an endpoint is a pod. You can simplify it like that. And a pod has different labels. And we're just saying that on the back end, I want only ingress traffic coming from pods with the front-end labels here. And in Go, what it looks like, you will define a structure in your operator or your agent with an ID, a set of labels, an identity that is actually unique, and a policy with a source identity, a destination identity, and if it's allowed or not. So basically, what you've just seen in YAML, it's now in Go, and we're saying and defining that who can communicate with who. And on eBPF side, we'll have a map of type hash, and we will load these policies saying, again, this source identity, this destination identity, and if it's true or false. And on the eBPF side, we will say if we want to let the packet pass or not, using, again, XDP, for example, with XDP pass or XDP drop, depending if the identity source is enabled or not. And it's just here a simple, not simple, sorry. It's just a log from one of the tools of Cilium that enables observability. And I just wanted to show you that we can see if the packets have been forwarded or dropped. And we're able to see and to observe on our cluster using Cilium all this networking stack, how they are behaving. And that's time to wrap up. eBPF lets you run safe, fast programs in the Linux kernel. You can use it for tracing, observability, security, and networking. And Go is actually the language of the cloud-native ecosystem in general. And with libraries and SDK like Cilium eBPF, for example, and you can actually load eBPF programs inside your kernel. And it's a perfect fit for Kubernetes CNI agent operators because it's very easy to integrate in any tool that you want to develop. I hope that you've understand some things. Again, it was an intro to eBPF. Now you have a sense of what is it. And if you are curious, you can visit the eBPF.io documentation. If I was you, I would start with the eBPF Getting Started lab. This is provided by Isovalent. It's free. You don't have to install anything on your laptop. You have a VM that is actually pop-up, and you can run everything. And there is a very nice tutorial with it, so you can get your hands dirty. So that's fun. Thank you. And I'm sorry for being late. Some questions before the apéro?
Yeah, so I have two questions actually. The first one is, why are eBPF programs, why are they only written in C? Is it just that that's where we have libraries to interact with the kernel? Or?
Yeah. Yeah, I would say that. But actually, so there is something that I didn't show, but in the wrappers from Cilium eBPF, you could bypass the C code and write only Go programs that are actually calling C programs. But I didn't show it here for sake of understanding more how it works, but you can do it, and it simplifies more the life of a developer, definitely. Yeah, so you can, but I mean, it's based on C, so that makes sense. Yeah. Exactly. Yeah, I didn't show how eBPF programs are actually compiled and verified, etc., but there is actually a whole process on that.
Yeah, so just second question, which is...
Oh, yeah, sorry.
How easy it is to shoot yourself in the foot with eBPF since we're running stuff at kernel level with kernel events and everything?
You can. Yeah, so you can. So there is actually the verifier that verify things that are working properly and that you're not doing things wrong. But for example, when I was actually building this demo, I was running on my VM. I was like changing the local host on the XDP drop, and I put like from outside of my VM, and then I couldn't access it anymore. Then I crashed my terminal. Then I was like, okay, I cannot show that depending on the context. So definitely be careful with what you're doing with eBPF.
Thank you.
Quick question regarding packet drop. Is it really impactful regarding CPU side? So let's say for a DOS attack, and the other side, on the attacker side, if I gain access to the machine, can I accept a packet which is supposed to be denied by the kernel or the EP table?
I don't think so. I would say no. If actually you put the deny policy on that, it cannot be bypassed.
And if you have concurrent access to the eBPF, let's say one says drop, the other one says pass.
I don't think it's actually possible
Okay.
to run these kind of programs that are doing concurrency stuff differently. One of the things that I'm thinking about is that there are some types of maps that, for example, you can't have several type of this kind of map. Let me rephrase it. You cannot have multiple types of map running on one host. For example, there is an arena map, for example, that is not possible. So there are actually ways to not bypass that by securing your system.
Okay, thanks.
Merci pour la présentation, c'était très intéressant. I'll do it in English.
That's fine.
I have a question. Do you need to install anything so that you can load eBPF modules into the kernel, or do any Linux kernel allow to load eBPF modules?
Yeah, you have some library to actually install like lib tools that are required to run your system. If you're more curious on the GitHub repo, I put all the prerequisites for the different example if you want to go further.
Okay, thank you. Because it is kind of scary to be able to inject code into the kernel, right? It gets access to virtually anything.
Yeah, so it can be, but it's always, for any tool that we are dealing with, there are downsides, and it depends how you use it.
Yeah. Thank you.
You're welcome. I guess we are done. If you have more questions, I'm happy to talk after. Thank you.